All right, I want to start off today with talking about the electric potential. All right, so the electric potential. It sounds like I'm about ready to say electric potential energy, and it's not. It's not the same thing, even though it happens to be measured in the same quantity. So there's some confusion. So what I'm going to do is I'm going to start off talking about gravity. And we don't really have an analog with gravity, but I think if we understand gravity a little bit, we can see how it becomes parallel. So let's start off with a simple object like a ball, and it's above the ground, so it's got a certain mass m and it's a certain height h above the ground. We would say that it has energy gravitational equal to the mass of the ball times the gravitational field of the earth, g, times the height. Right? So this is the gravitational potential energy. And so we can break this down and saying that this m times g, that's simply the force of gravity. So there is this field, this gravitational field that pulls everything towards the earth, and as a result of that field there is a force of gravity here, so F sub g. And so that's what this is right here. We just take our mass, we take the strength of the field we call little g, and we know that to be 9.8 newtons per coulomb here on the surface of the earth, or near the surface of the earth. And so that's the force of gravity times the height above that surface. So basically, if I were to let this ball go, it's going to fall and go faster and faster and faster, and then eventually crash along on the floor and potentially bust a hole through it. So I like to use the analogy that the more energy you have is the bigger hole that you can create. So likewise, I can talk about how that relates to an electric field. So if I were to have over here a uniform electric field, so let me go ahead and I'm going to draw like a floor, if you will. It's kind of weird to have a floor electric field lands, but whatever. And so there's going to be E field pulling down, or showing down like this. We'd say E is the strength of the electric field. That's similar to the G over here. So this is measured not in newtons per coulomb, but in, newtons per kilogram. It's going to be newtons per coulomb instead of newtons per kilogram. So again, just to review, this is newtons per kilogram, and this is going to be newtons per coulomb, which is the unit for charge. So if I were to go in here and place a little positive test charge right here, then what would happen is it would receive a force, electric force, and this would be pulled down. So this is the electric force. And then it also would have a certain amount of potential energy. So it's also a height h above. So we can use the analogy that the energy, electrical energy, would be the charge times the E field times the H, times how high up it is from that platform. So that would tell you like how much you would, how much damage you would do if it crashed into that wall, if you will. All right, so once again, this right here is going to be the force electric, and that's just going to be the height. So what we're going to talk about today with the electric potential is going to be a different quantity. The quantity here that is associated with the G times H. The G times H term is what I'm going to focus in on here. Likewise, this would be E times H. H just being the distance from where the charge is to where the source of that E field would be. So if I go back to this picture and I say, okay, here is a line, and anything on that line is going to have the same potential. So there's something about anywhere on this position, it's all the same height in the same field, so this G times H value is a constant for anything along this position. And if I would decide to put more mass in that spot, I'm going to get a bigger hole in the ground. And likewise, I have another line that kind of goes like this, and if I put my mass down here, then it's just not going to quite make as big a hole down here. And so there's a quantity about potential. So this might up here might be like a high potential. This guy up here might be a high potential. This down here would be a lower potential. And now I might even go on to further to say that right here would be zero potential. So that's what I'm going to get at here with this quantity over here. So likewise, I have a position here, and this would be a high potential, and down lower would be a low potential. Same argument here. So we're going to focus in on this quantity right here. This is what I'm going to call my electric potential. So this right here is going to be my my E field, and then multiply that times the distance to wherever's ordering up or figuring out or the origin of that electric field. So let's figure out what this is. So we're going to call the electric potential, so electric potential, which by the way is called volts, is going to be equal to the E field. And so, you know, we can say, all right, so we know what the E field is. So if we go like the force of electric force is going to be equal to the charge, Q, times the E field, which is very similar to the gravitational force is equal to M times G, right? So it's the quantity that you put in your field. This is the strength of your field, the quantity you put in your field, and the strength of your field. So if I rearrange that to solve for E, I get the force over Q. So I'm going to end up getting the force of electric force over the charge, and that's the E part, and I'll multiply that times the distance. I'll just call it R. Why not? So it's going to be a distance to wherever it would take to get to the origin of the E field. In this case, we had a big metal plate, whatever. Apparently, I have a positive plate up here, a negative plate down here, but I didn't show that. But it's just the distance to that object. So let's continue that. So electric potential is going to be Fe Q over R, but I'm not quite done yet. Let's go ahead and we're going to substitute in the equation for the electric force. So I'm going to put the electric potential, and it's not potential energy, it's electric potential, is going to be the K, the constant, 9 times 10 to the 9th, I think it's newtons meters squared over coulomb squared, times Q1 times Q2 over R squared, right? That's the Fe equation, and then we divide all that by Q times R. Well, this Q is the thing that's the origin of that field. This Q2 is like the thing that we put in that field. That's the same as Q2 here, so those drop off. So this becomes independent of what you place in your field. It's going to be solely dependent upon how strong the source charge is that generates the E field. And notice here we got R squared and R, so one of those goes away like that. So the electric potential is going to be equal to K Q over R. Okay, and there you have it. So that's the equation. Now notice it only has one Q. This is the source of your E field, and it only has one R. So the electric potential drops off not at a rate over 1 over R squared like the force does. It drops off at a rate of 1 over R, the inverse. So let's do an example. Let's say I have a positive charge here. We call this a positive 2 microcoulombs here. And I'm just going to pick a location. Okay, so one point out here, we'll call that point A. Another point out here, we're going to call that point B. So what I'm going to do is I'm going to say, all right, if I were to have a little positive test charge, okay, sitting right here at A, there would be a repulsion. It's going to feel the force here, and it's going to repel, and it's going to want to. And if I let it go, it's going to scream away, and it's going to be really, really high acceleration at the first, and then the acceleration drops off, and eventually the force gets so small that it's no longer going to accelerate. But it's going to pick up a lot of speed along that way, especially right at the beginning. And then out here is a little bit further, so the force is going to be weaker. So when it's being pulled away, it's not going to have as much speed about it when it gets out here farther and far away. So we have a position here, distance away from this positive charge. So I'm gonna go ahead and quantify that. I'm gonna call that R sub A. So we'll call that R sub A. And then I'm gonna go from here all the way out to here, and guess what I'm gonna call this? I'm gonna call it R sub B. So notice that R sub A is smaller than R sub B. So what I want to do is I want to calculate the potential difference. And all I'm going to do there is I'm going to take my voltage at B minus my voltage at A. And voltage is another way to say electric potential. That's all it is. That's what a voltage is. It's electric potential. So when I do that, I'm going to take my equation right here and say, all right, K and Q. Q is the plus 2 microcoulomb. The K is a constant, can't get rid of that. So it's just simply going to be KQ times, now in the parentheses here, I'm going to do final minus initial. So it's 1 over RB minus 1 over RA. And that's your potential difference to go from here to here. And so if I release an object right here and I let it scream away, It's going to get to here, and then I can, if I know what my potential difference is, remember the voltage is energy per unit charge, I can then determine how fast it's going to be when it reaches point B. If R here is going to be at infinity, what can we say about the electric potential? So if I set R, if I set my position here, and I move this position all the way out to infinity, I'm going to find that my electric potential is, in fact, 0. And that's right. So the farthest away you get, the less and less potential that you have. So anyway, that's kind of how it works out. I'm going to draw this another way, just to kind of put a cap on it. I'm going to draw it from its side view so you can kind of get a feeling for what that looks like, kind of like a graph, if you will. So what I'm going to do is I'm going to have an axis here, and then going across like this. This right here will be my point A. This right here will be my point B. This right here becomes my origin where my charge is located. And so we're going to call this axis the voltage, the potential as a point. So can you imagine if I take a positive charge and I bring it in close here, can you imagine how strong that force can get? I mean, it's going to be, if I get it like really like super duper close, it's going to want to scream away at a high rate of speed. That's going to be a huge amount of potential. So I'm going to go it's basically going to go to infinity at that location. And then it's going to drop off at a rate over 1 over R. And so when I calculate this right here, this height right there, that height, that point, that's going to be KQ over R sub A. That's how high that is. That's this height right there. And then likewise, I go over here and I have this height right there. Then this guy is calculated by KQ over RB. That's all it is. So I'm just going to get the difference from here to here. That's the difference in potential. That would tell me how much energy per unit charge that you get. So remember that the voltage, V, is the potential, which is going to be the energy per charge. And this will carry you very far in the land of electrostatics. Thank you very much and have a good day.